Good morning, everyone. I hope I had a good tutorial session yesterday. Any comments or any remarks from what you learned in the tutorial section? Any questions on them? No questions? All okay? Huh? Okay. I mean, if there are no questions, we will then move on. So I'll start somewhere here. Is that right? Okay. So let's just quickly recap what we have done so far and then move on from there. So, we started with, how do we develop simple discrete time population models. Okay. And then we thought, of course, there are so many processes that are relevant in nature, but we focused only on competition through resource limitation. That was the major, process that we considered. And then we thought, how does that influence the birth and death of individuals? And after accounting for those, we said, so the way we started off was that the current population, together with, births minus deaths, basically accounting for this sort of, led us, based on some assumptions, that the logistic population model. As I mentioned, it doesn't have to be logistic population model. It could have been Ricker population model, others, right? But this is the most very popular one. You also just hear the term logistic map or maps. So the discrete time population models, they're also known as maps in the nonlinear dynamics community. Basically, you map value of a variable at time t to the next time step, next discrete time step. And sorry, yeah. Why is it called logistic? Is that what you are asking indirectly? Yeah, that's an interesting question. I did not know for a long time. I think the answer is this, but maybe Kavita can correct me. To really know why this is called logistic model, we must really look at the continuous version of this. Okay, where this process is not true only for the discrete generations, but let's say if this one unit of time was an arbitrarily small unit, less than generations. In such a case, I will derive that today. In such a case, when you solve the equation, the functional form is called a logistic function. Okay, and that's why it's called logistic model. So it's nothing fundamental about it. It's just so that the functional form is a well-known function called logistic function. And that sort of, that name has carried over to the model itself. Okay, but there is really no logic, fundamental logic. So if you don't know why it is called logistic, it doesn't really matter. Okay, that's the answer, right? Actually, I think that dx by dt is equal to x into 1 minus x. If you solve x of t will be a logistic function of time. I think that's the reason. Yeah. So there is really no fundamental reason behind that. Yeah. Any other question? And Ricker population model is called so because Ricker developed the model, and that he did in 1950s. He was trying to explain fishery population dynamics, and then he observed some very weird dynamics, and he thought, why don't I write down some reasonable set of approximations and analyze this. He did not have all the mathematical tools available to analyze the model, but nevertheless, he pretty much got what people discovered much later in mathematics literature.
Like my question is, how accurate they are when we compare it to actual biological situations.
Okay, that's a great question. So it really depends on what you're trying to compare. So accuracy depends on comparing something with something, right?
Yeah.
Okay, so now This model may be accurate for some specific species, but may be totally off for some other species, right? So when we develop models, we don't often care about the accuracy of the model for any specific system.
Okay.
We're often interested whether the model provides some useful insights and some new ways of thinking about real system that we couldn't have gotten otherwise.
Okay.
So basically, in most cases, so there are two broad class of mathematical models that one can think of. Okay, one class of models are I'm really trying to predict what happens to midges next year. Okay,
Okay.
then the accuracy becomes very important. Okay, what happens to tiger population next year? In such cases, the accuracy of the model is really important. But in these type of mathematical models where there is no specified goal of explaining a a specific population, the evaluation is not based on the accuracy. The evaluation of model is based on many other factors, and one of them often is is it able to offer us some new insights that we couldn't have gotten by verbal arguments only.
Okay.
So if I told you this was the criteria, do you think this model is, how will you evaluate this model? Do you think this model was able to give you some new insights about how populations may behave under the conditions of resource limited driven competition? Do you think this gave some new insights that you did not have yesterday morning? It gave you some new insights. Does everyone agree, or only one person agrees?
This may, I don't think there is a certain way to know if this will or...
I mean, you can based on your experience. What was your experience understanding the model? Did it give you some new insights? For example, how many of you could have thought that competition can provide, cause cycles in population? A very well-defined cycles. How could you have all guessed it? I mean, I think somebody actually did guess, by the way. When you saw that Mitch graph, somebody said, yeah, maybe something like that might be happening, but those are rare. But for example, could you have predicted that, so I'm assuming that yesterday in the tutorial you also learned about something called chaos, if I'm right. What is chaos? Slightly more precise statement.
Randomness or noise?
Not really, no.
Okay.
In fact, it is called deterministic chaos. It's not just chaos, right? It's not randomness strictly. I mean, what you're saying is right, but I'm looking for a slightly more accurate statement of what is your understanding of chaos. Initial condition part is absolutely right. What is the implication for our understanding of populations if there is chaos in real systems? So why should I care if there is chaos in real systems? Okay. The prediction of next state becomes, the prediction of next state alone probably will not become very difficult because it's a one-step process. But you're right in a general sense that prediction over longer time scales becomes extremely difficult. Why is that so? So let us assume that there is actually if you have a real world population, prediction is very hard. All of us know. Why is that the case? Because there are many unknown factors. Processes are very complex. Okay. And something stochastic might happen which I have no idea almost by definition. Right? So prediction of real systems, which is driven by many factors, many unknown factors, and also stochastic factors, is obviously very difficult. Let us assume a very idealistic or a hypothetical scenario that there is one population of midges that follows this model exactly. Let's say it never deviates. It exactly follows this equation. Okay? I know it's a very ideal scenario, but that's, in fact, if it is true that there is a population that exactly follows it, isn't that really cool? Because it's such a simple equation, right? Let us assume that is the case. Let us also assume that by parameterization of data to the model, we find that R0 is 4. So did you all simulate this model for value of 4 yesterday? Okay. If you have done simulations, so we know that the system exactly follows this. this equation has no stochasticity. Okay, all right. So which means that our understanding of deterministic equations is that, if I know what is happening today, I must be able to tell you what will happen however long you wait, right? That's our understanding of deterministic systems, right? But consider this scenario if I have two populations where the initial population was x0 and another population where the initial population was x0 plus a small difference, delta. Two populations, but with very small difference in the initial conditions. What did you find in your simulations yesterday? If you simulate this for, let's say, 25 generations, what happened? Let's say this was 0.1, 0.11. And this delta can happen for a very simple reason. I have, let's say, gone and counted all the midges. And my friend there also went and counted all the midges. We found that there is a 1% error in our estimates. 1% difference in our estimates. We don't know who is right. But we both think, yeah, 1% is hardly a problem, right? Because that much of level of accuracy in two independent measurements is actually not a bad thing in biological system. And we have made these measurements, and we know this system follows this exact equation with this parameter value forever. Now we will both make predictions of what will be the population size after 50 generations. Are we going to agree on our predictions? What did you find yesterday? How did this go? So if you have done the simulations, you must have found something like this. So let's say this is x, t. So two of us now make predictions of what will happen to the system. So this was 0.1, right? So two initial conditions very, very close. So initially the trajectories will be very similar. But what happens after 5 to 10 generations? If you have done simulations, you will say that they'll actually begin to go totally as if they were never together when we started off. What that means is that even in a system that follows a very simple equation, deterministic equation, and if the system is uninfluenced by any types of unknown and stochastic factors, even in those systems, two people who made initial condition measurements will disagree about the state of the system after some even 50 generations. What does that mean? The system is extremely sensitive to the initial condition. And what is the consequence? Consequence is that we have very low predictive power. So we have very low predictive power because the smallest differences in our initial estimations can cause huge difference to our predictions of the future population size, which basically means that all my perfect knowledge about the system was basically useless. Yeah, I haven't used the word nonlinear. Yeah, true. I mean, so I don't know how many of you understand what is a nonlinear equation. So this equation which has, imagine this equation had only the, this term, where R0 xt without this term. The original model we first developed when we assumed that the R was a constant would be a linear equation, right? Because the future population depends on the current population with a multiplicative constant factor, right? But here it's a more complex function, and these type of dynamics occur only in nonlinear systems. Is that your point? Is that okay? Yeah. Yeah. Why does this happen? Okay, so that's a great question. I don't want to get into the detail. I think there are many explanations why it happens. So in some sense, the intuitive way of understanding it, going back to this diagram that we wrote. Right? So up to 3, so the system was going to the equilibrium, okay? But What happens beyond 3 is that R0, it is effectively a measure of growth, right? Is very high. So although system wants to reach this state, let's say if the system is somewhere here now, it wants to reach this equilibrium, because the growth rate is high, it often overshoots the equilibrium. Okay? And again now, so we had a low population, consequently high resource per individuals. So they all ate very happily and they all reproduced a lot, and therefore they overshot the equilibrium to these levels. Now again, now everyone has a lesser amount of resources per individual. So now the population will come down, but because they're already so high in number now, they will again overshoot the equilibrium. So because R0 value is high, they keep on overshooting the equilibrium. That explains why they don't reach the equilibrium. It doesn't exactly explain why there is chaos. Okay, so and this becomes more and more. This overshooting becomes even more and more as R0 increases, right? Because the growth rate is very high now. That's a very unsatisfactory but a starting point for the explanation. So nonlinear dynamics folks and physicists explain this using the idea of something called a stretching and folding in these kind of maps, 1D maps. But I don't want to get into those. I mean, I can recommend you references for you to read about them. So there's a phenomenon called stretching and folding, which is basically that, you stretch and again fold the system across the equilibrium of the system. And the stretching and folding, in fact, there's a very, very simple example. Imagine you are something called a baker's map. Okay, so the idea there is very simple. Imagine you have a dough, and then I don't know how many of you have made chapati. Imagine I make a square chapati. Okay, and then so imagine that I put a point here now. Okay, and then let's say I now double the size of this. So where will this come? It will come somewhere here. That is stretching. But imagine that I now fold this into half again. We do again, in chapati, we do a triangulation of some sort, right? But let's imagine I just do half of it. Now this point will come somewhere back, right? Imagine I keep on doing this. Depending on the rate at which I do, this point will either, reach an equilibrium state in the sense that it will always be at the same location over time. Or it actually can even exhibit, it can basically move all around like a chaotic, dynamics that we saw. If we plot the location of this point along the length of the chapati dough, so depending on my sort of, the extent by which I stretch and fold, this point can actually move all across the entire thing. So this stretching and folding dynamics is used to explain the idea of chaos in physics and nonlinear dynamics. If you want to read, you can read something called Baker's map, I think. I think it's usually used in, this is a relatively easy way to understand the mechanism. Yeah. So that's what I'm going to come to today. Yes. Yeah. So any questions on the discrete time models now? So I hope I have addressed your question in some way. So the purpose of mathematical models are many-fold. And in these type of simple models, the purpose is to see, does it offer some new insights that I would otherwise have not gotten? So imagine that if I had shown you mixed populations, in the absence of a modeling framework like this, I would have probably been at a difficult, it would have been easy to guess that entirely internal dynamics between individuals and resources can cause such really dramatic changes in population size, right? That would have been very hard to come to a conclusion without a modeling framework of this type. And if there is imagine if we had done some experiments with very close initial conditions, and if we had found very, very different outcomes even after a short amount of time, what would we often conclude? Maybe there is some kind of horrible stochasticity in the system. But what this model tells you is that, hey, look, you don't need to have stochasticity to have two very close trajectories diverge over time. Okay? So this provides alternative explanations, alternative ways of thinking about what we would have attributed to some other more mundane explanations. And therefore, these type of models are very helpful. Now, how do we really map it back to real world data? Does it really, is it the only purpose of mathematical models? Of course, as a starting point, it's not the only purpose. In fact, there are ways to test the predictions of these models. There are ways to see whether real world data exhibit these kind of patterns, but that's an entirely different topic altogether. And I will not I will not have time to go to those kind of questions today. Yeah, I think it's an excellent point. So let me now phrase whatever he said within the context of this model alone, which is that, so if we had a verbal model of how competition affects birth and deaths, and therefore how populations reach carrying capacity, if we had a verbal model, it does a fairly good job in many situations. However, those type of verbal models often miss a lot of important information. When we write down these equations, we have to think a lot more carefully of when are these forms of equations true, right? For example, I mentioned many other things yesterday, like, we have to implicitly assume here that the population is actually infinitely large. That is something not evident at all. And in fact, our verbal arguments also incorporate such inherent implicit assumptions that are not very evident. So another assumption we have to make here is that the system is well mixed, which means that any two individuals in the entire population has equal chance of interacting, which again is not evident even from the equation here, but only a careful thinking of how we wrote down the equations helps us. And verbal arguments are often very hard to capture those type of details. Okay, so those are the two simple examples of how many other assumptions are actually hidden here, and we probably haven't discussed many of them at all. Okay, and another thing is things like synchronous versus asynchronous birth and deaths. Again, I mean, as we will do right now, once we finish this discussion, what happens if the births and deaths were happening on a much smaller time scale? What will be the results? That small difference actually make dramatic changes to all of our results that we have found so far. Okay, but those kind of things are extremely hard, to sort of arrive at by verbal models alone. So in fact, I often argue that you need mathematical models only if you're not smart enough. If you're really smart, you can just argue everything verbally. Mathematical equations help us sort of stay grounded. And because once I have made up my mind about what are my assumptions, I'm going to stick to them, because these will make sure that I'm not violating the assumptions I made in writing the equations once I start using them. But often in verbal arguments, what we do is, we have made some assumptions, we don't even know what the assumptions we have made, and then when we start working through them, we change without thinking. And again, mathematical models prevent us from, doing those kind of unnecessary extrapolations that we shouldn't be really doing. Okay, that's why I think mathematical models are again very useful for us to think through very carefully. And they also offer many new predictions that we cannot come up with verbal arguments alone. I mean, I think he gave the example RK selection. One can think of similar examples here as well. Okay. Yeah. So, okay. I mean, if you're all happy with this, so, please do go and read the 1976 Robert May's paper. It's not the easiest paper on life to read. Okay. So it's not the easiest paper in the world to read. So you have to spend some time. So you will not be able to read the entire paper for sure. Okay. The second half is extremely difficult. But I think to some extent, I think maybe I can tell you exactly up to which section. I think given the yesterday's exercises and so on, you must be able to follow a good part of, I would say maybe 30 to 40% of the paper, one must be able to follow it now. With the yesterday's 3-hour sessions and some discussion we have had today. And also that paper again emphasizes how, if the title of the paper is, very complicated dynamics from very simple models, something on those lines, right? The emphasis is entirely on that. And it discusses what are the implications of that in model building, analyzing models in the introduction section, and then goes through some of the results of logistic model. But it does get very difficult beyond a stage. Once the results are presented, he goes on to discussing the mathematics behind them, and that might be not accessible even for mathematicians. So you don't have to feel very bad at all. Okay, but please go back and read the paper, and we can also discuss some of the aspects of the paper if you find anything interesting. It may give you some ideas for the project that Kavita has been suggesting you as well. Okay, so with that discussion, shall we now move on to continuous time population models? By the way, I hope that all of you yesterday, I did see that you have found all these things, right? So these are, as I mentioned, these are called bifurcation points. Okay, this is called a period doubling bifurcation, and this keep on happening, and the number of cycles here basically grow like 2 power n, and in fact 2 power n cycles of all n are actually found in an extremely narrow range between 3 and 3.58, I think. And in fact between 3 and 3.45 you have period 2 cycle. So between 3.45 to 3.58, just a window of 0.14 or so, you have all other cycles. So which is extremely hard to find numerically. And beyond that, you have many other cycles, many other complicated dynamics. Okay, so, and then I had also asked you, I hope you have had some time, did you also try applying all the techniques we have learned for the case of Ricker model? How many of you tried? Okay, that's impressive, around half of you. Did you find the same results, very different results? So for example, it also had a parameter called R0. So what happens to the population when the R0 is very small? By the way, broadly, do you find similar results, or is it totally off? Similar results? How many of you say similar results? Were you able to find the equilibrium? Did it also have two equilibrium? Were you able to do stability analysis for it? Were you able to find the equivalent of 0 to 3 in that model? Huh? What were the critical values in that model? What was the R0 at which the stable, the extinction becomes unstable? Sorry? 1 and E square. Okay. So R0 is equal to 1 in that model corresponds to this, which is same as the logistic model. R0 is equal to E square instead of 3 corresponds to period doubling. Right? Did others also find this, by the way? No? Have you tried? Please go and try. The only way you have understood something in mathematics is what you have learned. You must be able to apply it to a new situation. And it's not incredibly complex. The Ricker model is okay. And if you are stuck somewhere, Google Uncle will help you, because I'm sure there are many tutorials, pages online that help you solve Ricker population model. It's a very famous model. So you shouldn't be very hard to find. But please don't do that. Instead, discuss among yourselves. Often the best way to sort of fix the bottlenecks is discussing and figuring them out. Okay. Really, I really urge you to do this. Please do go and do this and find these bifurcation points. And you can, of course, do simulations, exactly like you did for the logistic model. Okay. And that requires you to only go back to the same spreadsheet and change the functional form. You don't have to do anything more, right? How many of you tried that? One person? Only one person? 2, 3, 4? Did you find the period 2 cycles there beyond these values? How much is E square? E square is around 10. Yeah, sorry, 8 point something, right? Yeah, 8-ish. Did you find period 2 cycles? You did? Okay. So, please explore that. And that way you get some confidence of understanding a new model where you don't know all the results. Okay. Okay, excellent. Now we will move on to continuous time dynamics. So just for reference, I will also write here is the modulus sign. This is to show that the df by dx is evaluated at the equilibrium point. If this happens, x star will be stable. Okay, otherwise it's unstable. Otherwise, meaning if it's the opposite, if it's greater than 1, that will be unstable. Okay, so in the continuous time model, we basically say that the births and deaths are not separated by exactly one generation, and because the age structure is really mixed in the population, anybody can reproduce at any point in time, and anybody can die in any point of time. So I don't really have a very clear separation of time scales. So therefore, we now have to write down how the populations change over arbitrarily small times. So again, this will depend on the current population size and the number of births minus deaths. Okay. So in the previous scenario, what did we do? We said that the births was equal to number of births per individual times the current population size. Okay. Now, because we have looking at a much shorter time scale, we must also scale this down by a time scale. Is that fine? Smaller the time step that we're looking at, lower the number of births will be, right? So likewise, deaths will be this. So if we take delta t to 1, we'll go back to the previous derivations we had. Okay. And so what do we now have? If I now substitute these two back in, so we'll have xt plus delta t is equal to xt plus b minus d times xt times delta t. So the only difference, if you compare your previous notes to this, is this addition of delta t here, which was equal to 1 in the previous case. Okay. Now it's a much smaller number than the one generation. Which step? This one? This one. So I have substituted b is equal to this, d is equal to this. The first term remains same. The second, so now the b minus d is b small b times xt delta t minus d times xt delta t. These two are common for both, so I have taken that as a common factor. So we have b minus d. Yes, in that interval delta t. A small b is the number of births per individual per unit time. Per unit time. So capital B is the total number of births in the entire population. Small b is the number of children an individual will have. Why? In fact, technically I did not make an assumption even there. If I had, so that assumption would mean that d is equal to 1, right? That of course is a very meaningful thing to do if I want to preserve the biological meaningness of the entire equation. So there are two ways to interpret that. I know d is equal to 1 is a necessary condition, or I can say I don't assume d is equal to 1, but every surviving individual has same fecundity or same probability of having children. Those are equivalent. So here I am clearly not making the assumption that it's a non-overlapping generation, because in fact this number is the largest one contributor. These will actually be a small contributor now. The births and deaths in a small amount of interval will be small. Yes. Non-overlapping generation. That would be a. I mean a small d. Capital D S would be equal to x. Yeah. So far, okay? So now because of this delta t hanging here, we will not do the same simplification we did before. What we will now do is, use the nice trick of calculus, which is to take this xt to the left-hand side and divide the entire equation by delta t, and then take the limits of delta t going to 0, and that will give me the left-hand side of So for those who have forgotten limits, calculus and all, I understand this might be, oh gosh, what happened? But don't worry. Focus on the bigger principle. So don't bother too much with the details of what does this mean. So this is the standard definition of the derivative of a function, right? So left-hand side therefore becomes dx by dt. D times x of t. I will also now move the subscript t as a function of time on both sides. Okay. So this forms the continuous time evolution of population density. This is the basic equation for. So what was the analogous equation in the discrete time? So we had xt plus 1 is equal to 1 plus b minus d times xt. Okay. But what we now have is a differential equation. So these are called difference equations. This is called differential equation. So let us make an assumption, a simple assumption that b minus d is equal to r is a constant. We call it r0 just to make yeah. Can you just say that again? No. I think I had just the way I wrote was a bit different. So I had initially combined 1 minus d and then wrote that as xt, right? Does it? I mean, just moving one term to the left and right. That the order of addition was a bit different, but I think everything else remains same. So, but one fundamental difference the way we read these equations are. So in the continuous time, we always talk about the rate of change of populations. And we write an equation for rate of change of populations as a function of the current population and time and many parameter values. In discrete time models, we write what will be the next population size directly. How are we doing on time? We have half an hour. Okay. So far, okay? Everyone with me so far? So how many of you have solved some differential equation in the recent past? Only. So when was the last time you saw an equation of anything like this? The others probably not at all or very long ago. Huh? So okay, so here is the way to think about this. So don't worry if you don't know how to solve the equation. I will do something very interesting about, so largely most population models are also nonlinear dynamical models, which means that they are very complex equations, which means that even the best mathematicians cannot solve them, which is a great thing, right? Which means that they also use many heuristics which are very easy to understand. Which is what I will focus on. I will not focus on the differential equation solutions part. Okay, and in fact there are just books written on how to solve differential equations. Undergrads in physics and mathematics learn one full semester course of how to solve differential equations. We won't do that, okay, because we don't need them. Even if you learned all of them, you will still be not able to solve many population dynamical equations. Okay, so you're in a good shape. Even if you don't know how to solve differential equations, it doesn't matter. Because some of the very simple techniques actually work really well here. Very simple and rather intuitive techniques work really well, which is what I am going to focus on. So if you have never solved this equation, it's fine. For this case alone, I'm going to tell you the result, but probably you know that already. So in the case that b minus d is a constant, what's the biological assumption of underlying this? it's equivalent to what we did yesterday again. What does this mean? If the B minus D doesn't change over time, it's a constant, it's independent of time and population density, huh? That's fine. What is the biological meaning of it? When is it true? Huh? Unlimited resources, right? So what this means is that I'm implicitly assuming, in fact, explicitly assuming unlimited resources. If this doesn't depend on population size or time in any way, it's unlimited resources, and of course there are no other external factors like stochasticity and so on. So in such a case, this equation now becomes dx by dt is equal to r times x, r0 times x of t. This is a very one of the simplest differential equations. So I'm just going to tell you the solution for this. Okay, so x of t is equal to x0 times e power rt. So all of you know what's an exponential function, right? So what this tells you is that given an initial population size, the later population will be an exponential function of time. And if R0 is negative, which means that B is less than D, the number of births are less than number of deaths per unit time, okay, per individual. In such a case, this becomes a negative number. Therefore, whatever the initial population you start with will decay exponentially. And it's exactly analogous to the case of R0 being less than 1 in the discrete time model. And if R0 is greater than 0, that means the births per individual are greater than the number of deaths, and that will lead to exponential growth. Is that fine? Any questions on this so far? So just if you just flip a few pages, this is analogous to geometric growth where xt plus 1 was equal to r power t times x1, and if r0 was that less than 1, right, then it corresponds to the exponential decay, and if r0, capital R0 there was greater than 1, corresponds to small r0 greater than 0 here. Okay. So I told you something yesterday, which is that whenever you write some new symbols, always think of the possible range of values this kit can take. What are the range of values that R0 can take? Can it be negative? Capital R0 could not be negative, right? But can small r0 be negative? Yes, because it's just birth rate minus death rate. So this can be negative, it can be positive either. So it can be both positive and negative. And if it's a positive growth rate, you will have an exponential growth. And if it is positive growth rate and is a constant, that will lead to exponential growth. If it's a negative growth rate and constant, you will have an exponential decay. Again, of course, extremely simplistic scenario of unlimited resources. Okay. So obviously this is not true in many cases. So how do we now account for this? How do we now, account for limited resources? What did we do in the discrete time model? I will just revise that again. Discrete time, we had a term that was equivalent, which was R. So constant was the unlimited resource, right? And then we all argued that R has, which is a measure of how many births happen, effective births over deaths happen as a function of population size. This must reduce in some way in any form, to account for the fact that there is competition for resources. This is what we did. Can we do the exact same thing now for the continuous time? Except that this won't be capital R, but it will be B minus D, which is the small r. So you remember again, this was 1 plus B minus D, but this will be just B minus D. Which basically means that birth and death now depend on the density of population. So the simplest case would be, this is density let's call this R0. And then what should happen because of competition for resources? This birth minus deaths will. Can it increase with population size if it's a competition, if it's limitation for resource? No, right? It has to only decrease. Okay. So let's again assume the simplest case of the straight line. Let us assume it intersects y is equal to 0 axis at k. So here is the thing. So we know the simplest case. Let's say if somebody comes and tells you, I'm looking at this quorum sensing bacteria, they do these crazy things. They don't really like to grow when they're small in numbers, but the moment their density increases above some threshold value, they really produce some chemicals and therefore their growth rates increases. If you incorporate all those, the density dependence will be different. So what you have to really think is, given a biological scenario, you have to convert that to how this R changes with density. For the simplest case of competition for resources, I have assumed it's a linear decay. It doesn't mean that for every scenario that would be the case. Okay? So, yeah. What do you mean initial value? R0, yeah. It's not going to K, it's going to 0 at population density of K. Yes. Sorry? Yeah, once he completes the question. You can actually use the mic, it's right in front of you.
My question is, since now it can take, this R can take any value as we were discussing just now, so will it start from R0 in this scenario, like when we are drawing?
I mean, again, depends on you, your assumptions. It could depend on something else, absolutely. I think that says it has to start from R0. I am assuming it starts from R0. I'm assuming that when the population density is very, very low, the number of the per capita, the change, the difference in the rates is given by R0. That's my assumption. But if you have reasons to say that it's a bit different, sure. It's also my assumption that this decays linearly. It doesn't have to be. Okay. Any other questions? Okay. So basically the task of converting the underlying biological process to how this function look like is at your hands. As long as you can justify, that's fine. And in the process, you will make some assumptions, and which again, as long as you're very clear about them, it's fine. Okay. So if this is the case, how does R depend on X now? R will be 1 minus. By the way, I had asked some of you who may not have done for something like this, did you go and verify that the equation that connects this actually is given by this? Okay, I hope you have done. That's good. So now, can I now substitute this into the model here? dx by dt is equal to b minus d times x, and b minus d is, okay, nothing but this under our assumptions. So therefore dx by dt is given by. So we now have a new model that explains how populations grow under the constraints of limited resources. Okay. So how many of you are from microbiology background? Several of you. So you have heard of the specific growth rate, right? So in some sense, this term, this R that depends on this is also called the specific growth rate or the per capita growth rate. Okay. So R is nothing but ecologists often refer to this as per capita growth rate because this measures how an individual will reproduce. What's the birth rate minus the death rate of an individual. So effectively the individual growth rate. So always remember that this small r measures the growth rate at the level of individuals. And this r times x measures the total population growth rate. Okay. So what is the, again, total population growth rate is per capita growth rate times the total population size. So always remember to distinguish the total population growth and the per capita growth rate. Okay, and the equations we write is for the total populations. Okay, which will depend on the individual growth rate times the total population size. So this is an assignment I had also given you yesterday, which is exactly the same. Find the equation of a straight line that connects, 0, R0 with k, 0. This straight line is nothing but this. Y is equal to mx plus c. If you use that, and if you input 2 coordinate values, you should be able to solve the 2 parameter values there. Yeah. I'm sorry. So I'm abusing notations here. Is that what you mean? Okay. No, this is also per capita. This is also per capita. Absolutely, yes. Yeah. So, so in your microbiology questions, you often hear the per capita growth rate of this cells or bacteria is some number, and it grows from this to this, and you're asked some period doubling time and so on and so forth, right? It is in this context, under the assumption that this is a constant. That's what you're often doing all the calculations. But the idea of per capita growth rate applies throughout. So although you solve questions only in the exponentially growing phase, but the idea is true across. The moment the resources become limiting, that per capita growth rate will change with density. Okay. So the specific growth rate in this model is true only for low population sizes. Any other questions? Okay. So anyway, we have now written the new differential equation, which is more complex than the previous one. Okay, yeah. Why am I not using? Let us say if I did use exponential function. How will that look like? Let's say something like this. No, I will leave that as an exercise for you to think. Is that okay? Technically, there is nothing that prohibits as long as you write the exponential function correctly. But you can certainly, I think, do that. Yeah. And sometimes some of these are driven by mathematical conveniences also. So. Okay, so we have a new differential equation which is more complex than the previous one, where here we know the solutions very nicely, very easy to interpret. Okay, standard textbook stuff, but this becomes now more complex. Okay, how many of you have seen this equation before? Have you all done a population biology course? Is that where you saw? Where else have you seen? It's the same. The context is exactly same. Yes. Okay, where else? Huh? Systems biology. Yeah, again, the same context, I suppose. Yeah. Where else? Huh? Oh, I just solved differential equation. Huh? I mean, in your 12th class, probably there will be some chapter on differential equation. You will be asked to solve this equation by method of, take the partial, what is it called? I forgot the name now. Partial fractions, right? And then solve it. Yeah. Okay. So we will not do that now. So in fact, it is possible to find a solution for this equation like the way we have done there. I mean, like the way I wrote down how x depends on time, but we will not do that. We'll use an entirely different approach to understand these equations. Okay. We will first start. So again, remember what did we do for the discrete time case, discrete time models? Once we had a model, what did we think about? We thought about the concepts of equilibrium and stability. Can we do something similar here? Huh? We can. So how do you define an equilibrium? So let's now think of a general model, which is dx by dt is given by f of x. Okay. So this was true under the condition of computation for resources, right? Maybe in a different system, many other factors come into play. Maybe mutualism among individuals might be also important. Maybe some other effect of anthropogenic factors might also be important. Therefore, equations can become even more complex. So a general equation can look like this for a single population. So how will we define an equilibrium? What's the meaning of equilibrium? No change in population sizes. What does that mean in terms of this equation? Which term here becomes, what becomes 0? The left-hand side becomes 0, right? So in the discrete time case, left-hand side became equal to the right-hand side. In this case, the left-hand side basically becomes 0. Okay, so equilibrium corresponds to populations do not change, which is, how do you find this? By finding all the values of x star where f is 0. So all values of x star where the function f becomes 0 will be called equilibrium. Is that fine? Now, so you remember we defined the notion of stability. What was that? We start with an equilibrium and make a perturbation. The perturbation expands. That will be stable equilibrium. Is that right? Or unstable equilibrium? Be unstable equilibrium. If the perturbations decay and come back to the equilibrium, those will be stable equilibrium, right? So we want to know which of these equilibrium are stable and what would that correspond to. And so I did not derive the mathematics behind it. How we got the condition. If I were to do exactly same steps, and we will find that a similar quantity has to be basically less than 0. So the modulus of this quantity was less than 1 in the discrete time case. For the continuous time case, we don't take the modulus. We just take the actual value of the derivative at the equilibrium And we find when is that less than 0. Whenever that is less than 0, that equilibrium will be a stable equilibrium. This would imply X star is stable. Okay, so we have 5 minutes. Now you have all the methods at your disposal. Can you find out equilibrium solutions of this model and find the stability? The analysis is actually easier than the previous case, by the way, so you must be able to do it pretty quickly. So I will give you 3 minutes to do this, and then in the other 3 minutes I will do this. So what you need to do is basically, for the logistic model, the f of x is actually this function. Set that to 0 and find all the x values where it becomes 0. Once you have found that, take the derivative of the function and then plug the equilibrium values, and then apply this condition. So in microbiology like courses, do you also do stability analysis and all? No. Do you? I mean, somebody said you learned this in microbiology course. Do you guys do our systems biology course? Do you do stability analysis of these type of models? Solving, sorry? You do learn that, is it? Okay, excellent. And some of the techniques, I think Kavita will be using when she teaches population genetics models. Is that right? These 3, right? Exactly same. Okay, great. So X maybe becomes allele frequencies instead of population density, right? So yeah. And that's the usefulness of mathematics. Although derived in some context, they're often very portable. Yeah, they're basically same conditions if you just work them. Yeah. Okay. So I'll just do it for you all. I think I have seen the first row here, and I have a representative idea of what people are trying to do. Let me just do it for you. Let's solve this. Okay. So for the logistic model, f of x is given by r0 times x, 1 minus x divided by k, right? And then how do you find the equilibrium now? Say f of x star is 0, which basically is setting this to 0, r0 x star is equal to 0. So one mistake I saw some people doing was to set r0 is equal to 0. When we are solving an equation of this time, we always look for the variables. The variable of interest here is x, which is population size. So we must always solve for these, not for the parameters. So understand the difference between a variable and a parameter, right? So when will this be 0? You can either have x0 is equal to 0, or this term is equal to 0. So that means this is one possible equilibrium. If the x0 is equal to 0, the entire term becomes 0. Or if this becomes 0, again, entire term becomes 0. What does this mean to say this becomes 0? This is same as saying x star is equal to k. So the two equilibrium solutions of this model are population size equal to 0 and population size equal to k. And again, think, does it make sense? If I start with population size 0, it doesn't change. Makes sense, right? And in this model, if I start with population size k, this term becomes 0. Therefore, the rate of change becomes 0. Again, it makes sense. So two equilibrium do make sense. Now we have to understand what are the stability. This is the equilibrium part. Okay. Now everyone okay with this? I think at least almost the entire first row were able to do this part, and some of them were still doing the stability part. So how do you do the stability? Look at function f of x and take the derivative with respect to x. Okay. So one small mistake I saw people were doing was confusing dx by dt with df by dx. Don't do that. So the right hand side is f. Take the derivative of this with respect to x. Okay. So df by dx is equal to derivative of this, which we did yesterday, by the way. It was exactly same equation for the logistic model, logistic map, which was discrete time. That would be R0 is the first term. Second term will be minus 2R0 x star over k. This is the general expression for the derivative of f. So remember, this derivative is not with respect to time, but with respect to x. Okay. Once you have done, what you should do is you have a list of equilibrium and input each of them one by one to this expression. Okay. So let's look at the equilibrium 1, which is x star is equal to 0. If I consider this, what would be the df by dx? So R0 remains R0, but this term becomes 0. Is equal to R0. And for this to be stable, this has to be negative. Right? That means so I'm applying this condition here. Okay, does it make sense? So x equal to 0 means no population. That means even if I add a few individuals to this population, this system, it comes back to 0. And when is that true? When R0 is less than 0. And what is R0? R0 is B minus D. B minus D negative means deaths are more than births for a given individual. Probably the death rate is given more than the birth rate. And when that happens, of course, even if we add a few individuals, they're all more likely to die than giving birth to children. Therefore, eventually, they will all die out. That makes sense, right? And conversely, is unstable if this is greater than 0. That means if the B minus D, number of births minus deaths, if that exceeds 0, and if there is an area with 0 population density, if I add a few individuals, they will just grow to larger and larger values. Therefore, x equal to 0 is an unstable equilibrium in that case. So both of them make intuitive sense, right? So when you solve, also see what are the parameter values and does it make intuitive sense. Okay. Now apply the same set of criteria for another equilibrium. So this doesn't tell me anything about, okay, this makes sense. This tells me that x0 is unstable for R0 greater than 0, but where does the population go? It doesn't tell me that, right? So I have to look at the second equilibrium, x star is equal to k, and then evaluate df by dx at that equilibrium. What do we find? R0 remains R0, x star is equal to k, so this is 2 minus 2R0. So it's R0 minus 2R0, it is equal to minus R0. Okay, so now this equilibrium will be stable when this term is negative, which means when minus R0 is negative. What does it mean to say minus R0 is negative? That means R0 is positive. Is that right? Minus R0 will be negative when R0 is positive, right? So this implies that and the opposite, when this is unstable, when minus R0 is positive. Huh? Positive, when it's unstable. If R0 is negative. So in fact, they are just opposites of opposite conditions. Okay? Which means that when x0 is stable, k becomes unstable. When x0 is unstable, That's precisely when K becomes stable. Okay, so if I were to now write R0 on the x-axis and the equilibrium population size on the y-axis. So for R negative values, 0 will be the stable equilibrium, and K will be unstable. And for R0 positive values, 0 is unstable and K is stable. I hope everybody can see up to this. Okay. Yeah. What do you think? So his question is, have we lost all the chaos and cycles and stuff? So because this is leaving me low, is there a value of R0 when both of them are becoming unstable here, like in the previous model? No, right? If this is stable, this is unstable. If the other is unstable, the other is stable. So they are just opposite of each other in terms of the stability criteria. Stability. Is there a case when both of them become unstable, like in the logistic discrete model? No, right? Because this is stable for all values of R0. And therefore, the answer to your question is an affirmative, which is that we always have a stable equilibrium of K here for all values, and therefore we do not have chaos here. No cycles. Yeah. So he has a follow-up question. If we discretize, we go back to the previous model. How did this magic happen? So what's the difference, biological difference between discrete dynamical equation and the continuous dynamical equation? Was everyone able to hear his fairly succinct and nice argument? No? Because the births and deaths are instantaneous here, this effect of how the per capita growth rate changes with X is effective instantaneously. The moment population size increases, the effect on the birth and deaths of those who have present is instantaneous. In the discrete time model, they had to wait for a generation, right? So all the population increase happened in that duration. And therefore, the dynamics are fundamentally different. So in some sense, a biological term, if we have to sort of say the discrete time models represent non-overlapping generations, and that are whereas continuous time models represent biological populations where the birth and deaths are happening all the time in an asynchronous fashion. That difference alone can potentially cause a huge and dramatic changes in the way they behave. All else being equal, that difference of synchronous reproduction and death, and or in other words, overlapping versus non-overlapping generation, that difference alone can cause such a huge difference. Yeah, as I said, the one way to interpret, is that it is a non-overlapping generation. So you can have an overlapping generation, yeah, that's true, but you have to add an additional assumption in that case, which is that every person who is alive now, even if they were from the previous generation, have the same birth and death rates as the newborns. So that's often unrealistic for many species, right? So if I were to really apply this to biological populations, non-overlapping generation is almost a necessity. Yeah, so we can continue discussion over the tea because some people might be very hungry. Perhaps, huh? Okay, okay. Yeah, and I will resume at 1:30, my class at 1:30, okay. Yeah, it's the same schedule as yesterday.